Viva José,
Olá, viva.
viva. Podias pôr a gravar só depois, não? Não sei.
Eu pus a gravar automaticamente.
Ok. Ainda há aqui uma questão que não chegámos a falar do vídeo, mostras tu depois?
Há um problema, depois eu explico.
Ok,
Ok.
ok.
Sim, sim. Hi there.
Okay, so I think we can start. So good afternoon to you all. Thank you for your participation at today's webinar. We're going to have José Faria, research fellow from the TRUSTID project, presenting the work, together with Pedro Martins, a senior researcher at ISR at the University of Coimbra, to present the work on online student identification with face recognition that we've been doing in the scope of the TRUSTID Erasmus Plus project. So thank you all once again, and José, please feel free to start.
Give me just a second. sorry, my apologies. I was having some issues with, oh, let me go back. Sorry. Okay, so hello everyone. Welcome to our webinar about online student identification with face recognition. So COVID-19 has been a massive challenge for traditional institutions, which traditionally have been mostly face-to-face learning, have used a face-to-face learning model. For a brief time, they were forced into a fully online education model, which became a significant challenge, but mostly because they didn't know how to ensure how we could ensure integrity and fairness in the assessment process of online exams and other types of evaluations. And so this is where, and this is where online proctoring systems come into place. So an online proctoring system is any type of system which monitors students during an evaluation period, during an exam, during some kind of small test. These types of systems can have either human proctors and be manually have some type of manual review, or they can be partially automated or fully automated, where some of these features can actually just be managed by the system itself. Generally, we can find some common features among these types of systems. They'll have some sort of authentication, usually using the credentials of the university. So allowing, for example, single sign-on from the university. Generally, they'll try to limit what the user can do during the exam, or at the very least, they'll be able to detect and report any type of suspicious behavior. So they'll detect all of this suspicious behavior and be able to report to the person that is the proctors that will be hosting the exam, and be able to recount every type of encounter. And usually they'll also allow some sort of recording or extensive log to allow the proctors to manually review all of these suspicious events and try to determine if they were false flagged or not. Some also provide some integration with higher education institutions, for example, the login, like the login system that I mentioned, but generally these are very limited and are only possible for a few learning management systems. Generally, this type of integration is very limited, as I mentioned. At best, I think you can hope for is just some login management. Some might actually provide some reporting, but it's, as I said, it's very limited. Out of all of these systems, very few actually provide continuous user authentication. So, for example, when you sign into the exam, you just show your government issued ID, and usually that's going to be it. They'll just try to see if you've left the frame, if you got up and went to somewhere else. But generally, that's about it. You don't have a lot of very complex systems for authenticating the users. Most of these systems don't really implement any type of privacy preserving mechanisms. So you'll usually have to rely on these third parties to manage your data properly, which is a very big problem, because as we all know, there are data breaches all the time. Every year we have a massive data breach. Especially if, for example, we've had Facebook data breaches. We had an extremely serious one with LastPass, where a lot of their credentials were leaked, and so ideally we would want to implement some kind of mechanism to prevent when these problems occur that the user data isn't compromised or try to minimize the impact that it would have. Additionally, most of these platforms are browser-based, and so they will have limited monitoring capabilities. Either they will work with a browser extension, or you'll have to go into a web page. And so obviously, you're going to be working within the bounds of the browser. And so I could, for example, open PDFs or other type of applications in my other monitors, and usually I should be able to get away with those types of behaviors. And so this is where TRUSTID comes into place. So TRUSTID is a project that proposes a development of an open source and cross-platform framework solution for proctoring systems. So the idea here is developing a full server client architecture where we can enable the continuous monitoring of students and provide a very seamless experience for proctors to be able to monitor an exam without any problems. So we're actually using for ensuring that we can actually monitor the processes properly, we're actually just using desktop application. So we will have applications in both. Currently, we're only supporting Windows and macOS. So we have desktop applications. We are native desktop applications, which we are using to monitor the processes that the person is running, so that way we can actually analyze and make sure that the user isn't engaging in suspicious behavior. We're also taking into account that we are developing a very privacy-preserving framework. So what does this mean? This means that we want ideally to minimize the amount of information of data that we are sending from the user to our servers. So ideally, everything would be either on the client's computer or on the higher education institutions, which will have obviously the student information. We also want, ideally, to provide a better integration experiences for these higher education institutions, so they can use this more easily and be able to analyze the reports that we provide them. And we want to provide proper guidelines so that people will know how to actually use not only our system, but other similar systems, being able to interpret how we actually, how they should handle like these types of events of suspicious behavior, and how we can actually provide a good experience for distance learning. However, but how can we actually achieve continuous user authentication? So we need to actually go back a little bit and think about what do actually users, most students will have access to. Generally, we can assume that they'll have access to a PC or a laptop and a smartphone. These are two very common devices that people have. And so we can generally assume that you'll have access to a camera or a microphone. But how can we use this for authentication? Well, for this, we need to go into the realm of biometric authentication, which is simply refers to authentication based on biological characteristics of the users. Here are some common examples of authentication which we can find on our systems. So for example, facial recognition. Many people here probably have an Apple device, for example, an iPhone. iPhone is very famous for their Face ID, which I think has been introduced for the last couple of years on nearly every iPhone. Some higher end laptops might also have, if they're Windows-based, they might also have Windows Hello, depending on the camera system that they are using. We also have fingerprint recognition, which nearly every smartphone from the last 2 to 3 years has probably some kind of fingerprint recognition, even the lower hand ones. We also have speaker recognition, which is basically trying to model the speech patterns from recordings of the user. This is a little bit, this is less used, although we can still find some, some uses of this. Particularly, I don't know if anyone has a Google Pixel, but this can also be used, for example, for speaker recognition, so that you are able to, for example, transcript conversation and identify which user is actually saying what thing, which is a really cool feature if any of you have actually had the opportunity to try it. And then you also have a little bit more an esoteric authentication process, which is interaction-based recognition. So interaction-based recognition is basically a behavioral analysis of the user's behavior engaging with the application, where you try to, for example, analyze their keystroke patterns or the way that they handle the application, where they're clicking, where they're how they're using their mouse, and try to use that to try to evaluate if it's the same user or not. Like, this is a big research field. But it's usually not as common, especially in these types of proctoring systems. So generally, what we're going to be able to find is just the usage of face recognition and speaker recognition, which is what we're actually using in our system, which are the most stable and the better implemented ones. The architecture looks something similar to this. So any client will just download their application on their computer and is able to seamlessly log into the system using the credentials from the university. They'll log in, they'll do their exam, and then they're out. The only thing they will need to do, however, is the first time they will need to do an enrollment, where we'll actually build the models to with their biometric data to identify them, both using voice samples and face samples to create the models for speaker recognition and face recognition, respectively. On the LMS side, this provides seamless integration via reporting features. So the idea is providing detailed reports of every event that happened, every suspicious behavior, when did the user open applications which he shouldn't have. Basically, a very verbose report of every single event, so that the proctors can look at it and try to determine if the user has been cheating or not. Next, so for this presentation, we're only going to be focusing on face identification. And for this, I'm going to pass the word to Pedro, which is going to be detailing a little bit more about what we've been doing and what we've been implementing.
Okay, thank you, Jose. Can you just release the share for me, please?
Yeah.
Thank you. Just a second, sorry. Okay, sorry, I'm having trouble sharing. Can you see it? No. Strange. Okay. Okay. Everyone is seeing, right? I hope so. As Jose has said, we are our goal in the project is to develop a biometric system that actually uses image or video as an input, contrary to other systems that exist that uses other kind of features. So our goal ultimately is to identify users from a set of examples that usually are given on the enrollment stage that Jose was mentioning. Although our system has a set of constraints. First of all, it we are mostly facing with consumer-grade cameras, which usually have a low resolution images, typically VGA images. They have a lot of noise and usually poor performance on low light conditions, which is a limitation, a huge limitation for any algorithm, to be honest. Moreover, we actually have a set of computational performance limitations because we don't know for sure which machines run this software. So we need to select algorithms and solutions that can be as accurate and reliable as possible, and although being lightweight. So this is actually our main limitation, is this part. Okay, and ultimately, since we are dealing with an authentication method, this method needs to be as reliable as possible. So this is very important, so that we cannot give access to the wrong people, of course. And okay, I'll be showing. I'll be giving an overview of the system, the computer vision and machine learning system, on two major versions of the system. And in the process, I will be talking about face recognition and face verification, 3D head pose estimation, and our face verification approach, which is an approach that in fact delivers the identity to the system. So this is our first approach, which is the most simple and which is probably the first how can I say? Okay, this is the first approach that we developed. So we grab an input image, and after that we need to run face detection. In this case, actually the most known face detector is the Viola-Jones. In this case, we actually use a different approach. Once again, because of the computational issues, we actually use a template-based matching algorithm that uses OG features and is built by a linear SVM. So this template actually scans the image, and when the given score is provided, a possible solution, a possible detection is given. So we actually only detect the one image, one face per image, because our system has our system was targeting to set if more than one people is present. So only one detection is admitted, and this detection actually provides a region to the input of a neural network. Of course, this is simply a resize in this case, and the network that we're using is a ResNet 18, which is once again which is a network that is a bit of balance between performance and computational performance and accuracy. In this case, we are using a cross entropy loss function, so we are dealing with a multi-class classifier, which is in line with our problem. So we actually in a previous training stage, we need to assemble a user's database, the enrollment stage, and we perform this pipeline. And after having a trained model, we deploy the trained model on the client side, using only the inference, of course. An important part of learning the network is the data augmentation. So while this is a bit standard, in this case, I would like to mention a few things. the most usual approach is actually for each example, like this one, we grab an example over here, and this example, for instance, let's suppose we want to add some translation. Most machine learning toolboxes actually shift the image and then add a region with zeros on the known parts. So let's suppose I'm shifting the image to the right. On the left will be a black line without information. In fact, we actually do something different. We go back to the detection and we manipulate the region so that we always get valid information. This, of course, makes a huge deal on the performance later, okay? So that's the reason it's here, okay? Okay, this is a light demo of the system running on a subset of a known database, which is VGG faces. So you can see that the approach is, this simple approach actually performs quite well. However, let me just move up a bit. So this is running on each image at a time. And on the right, we can see the normalized image and the inference over here. Okay. Okay, of course, you can run it on video simply by running the system frame by frame. And this is the performance of this version, okay? And this is a system live with other people. Yeah, you follow the idea, I think. So, so until now, we actually have a system like this. This is a classical face recognition system. Although this is a problem for us because every time we need to add a new user, we actually need to get the data for everyone so that we can learn the network together again. So this is a huge limitation for this kind of system, although it performs quite well. With this in mind, we actually moved to a different approach. Instead of using a multi-class approach, we actually use a system that performs, tries to decide if the person that is seeing belongs or not to just a single mode of information. And this is called face verification. Notice the difference between, we just need to check if this sample belongs to this class of examples. Contrary to the first approach where we need to match each example against everyone. Okay. So this is our 2.2.1 version of the system that is where the initial pipeline is the same. So we use the same kind of face detector. Although right now we have a more elaborated system that first detects the facial landmarks. This facial landmarks serves two purposes. The first one is to get a more accurate, a more tight normalized image that once again serves as input to the neural network. And in this case, this actually we are facing in here with the similarity transformation. So the image, we have a sense of scaling and the rotation to extract this normalized image, where on the first approach we don't have. The second issue that is run by this model is the ability to deliver 3D poles in this, which is useful for a few things. To get 3D information, we actually need a 3D head model, which is represented here. And I'll be talking this a bit later on, but please keep in mind that the model is able to get 3D poles, so 6 degrees of freedom. And okay, and right now the inference part, instead we have a more complicated network, which is a ResNet 34. I didn't mention before, but the ResNet was okay. It was selected because of the computational issues, but this actually works quite well because I should say first that the ResNet is a network that tries to reduce the amount of fully connected networks, but although it adds residual connections, so that the gradients will be propagated with more that carrying more information. That's the source of its performance and accuracy is those issues. But okay, in this case, to deal with face verification, we actually learned the network using the so-called triplet plus. This will provide the output of a given image, a vector, in this case, having 128 values, which represents attributes of the face. Using this kind of vector of attributes, we actually query the statistics from those attributes, from the training images from that specific user, and decide if this sample actually belongs to this distribution or not. More details later, okay? Okay, comparing these two systems, from the privacy and the computational performance point of view. By the way, privacy in here is related to the computational performance because the amount of work that needed to be done either on the server or on a client. So the first approach, and in this case, since we didn't know which kind of target machines are being used, we decided to move everything that we could to the server, which is at the time a fair approach because we didn't know, once again, which are the targets. So the clients, so the application that people install on their side, simply grab information from the web camera and run detection. The detection is quite fast, so we left this part on the client. Everything else is run on a server. So image warping and both the training and the inference of the network is done on a server, and at the end the identity was provided back to the client. Although this is a valid solution, but it breaks on the privacy side of things because the server actually knows everything about the client using this configuration. On the second version, the server is only concerned about user login, so user management and login. Everything else is done on the client. By the way, everything that I described earlier is done using only CPU on the client. So we made a huge effort to make sure that everything works smoothly, even in old/normal machines. okay, including the inference of the network, okay. So I talked about the learning with the triplet loss. So what's the issue with this? So the triplet loss actually operates different from the multi-class loss, like the cross entropy. So let's suppose we have a batch of images on the input with 3 samples. So these samples actually have they have 3 categories. One is the anchor, other is a positive, other negative. So the anchor is a kind of a reference. Positive is a sample which belongs to the same class of the anchor, and the negative is someone from other class. Okay, so in fact the network tries to minimize this expression. So okay, the max over here is just to have, so is the max between this value and 0. So the max is only to have positive values on this loss. And we have 2 terms. So the first term is the distance between the anchor and the positive, this part over here. In here, this is a simple approach only using a L2 norm. And this part is the distance between the anchor and the negative. So by looking on the equation, we can see that the network tries to minimize this distance, so tries to approximate the positive to the anchor, while tries to move away the negative from the anchor. So this is more or less what's going on the learning. So, and then we grab another batch example, do the same, and continue, do it thousands of times. And after a while, we will get in this case, in this simple example, the 2 classes separated. So this is the intuition of how this works. But keep in mind that the network does not provide which one is it, okay? By the way, there's also a term over here which we call the margin. This is an offset that operates like a slack. So it means that if this is too large, it means that these 2 clusters could intersect. Okay, this of course larger the margin, more easy is for the network to separate things, because it allows to mix some examples. Let me move on. Okay, so at the end, eventually we get all examples somehow clustered in groups, and that's in essence what the network needs to then. But in fact, we are actually using a network that was trained on 3 million images. So we assume that the network was just by itself able to learn its characteristics and is able to make clusters on given facial attributes. So we actually, the learning of the network isn't done by us, is simply we just do inference, and with those inference we actually get information about a few samples. Those samples in the training stage are learned, so we need to learn this distribution. Let's suppose that we have this is our identity from one example, and we want to try to decide if this example belongs to the class or not. So we have actually two possible solutions. So previously we learned the mean and the covariance of this distribution, and by simply computing the Mahalanobis distance between one example and the other, and thresholding the distance, we are able to easily decide if this belongs or not to this distribution. Okay. Moving to the other part. So the head pose. The head pose is actually used in the system to validate images on the enrollment stage. So we need to know which are the images that carry more information. So more frontal images carry more information, will be more suitable to training, contrary to other possible poses that in fact the most extreme poses will be discarded. But once again, the system needs to be aware of that. So we have a model to do it. How this works? So we have a 3D model, as mentioned. The idea is to minimize the difference between the projected features of the 3D model and the 2D features of the face alignment. And this is actually a nonlinear problem where we aim to estimate the three angles of the rotations and the translation vector. And this is in fact solved with a Gauss-Newton approach, where the first iteration is given by the DLT algorithm. So I have a video showing the system working. It works quite well, actually. By the way, when we let me just go back a bit. Usually, when we are dealing with these problems, we need to know the camera calibration parameters, usually the focal distance and the central points. Of course, we don't know anything about that, but we can do something differently. We can use a model that has metric information, and by using that, we actually were able to estimate a scaling factor related to the focal distance. And with this information, we actually are able to determine, with some error, of course, the distance between the user and the camera without having calibration. Okay. Okay. This is the final part. We actually are working on an improved version, which will be called, we eventually be the third version of the system, where in essence, we are improving the input of the network. So the input, instead of being just a tight warp like before, is something else, okay? And this is so-called a piecewise affine warp. So in the right, we have the input images, and on the left will be the output. So the idea over here is to first to detect these locations. And after having this, we need to perform a so-called linear triangulation. And this is in essence a texture mapping process where this reference is fixed and is built with respect to the input of the network. Okay, and what's the advantage of this is that first it removes the influence of backgrounds, so no more influence on the places where people are, and more important, since we are aiming to identify identities, this process actually is able to cancel out expressions. So people smiling will appear on the left with the smile reduced and so on. So that's the deal with this. So, but this is of course it is work on in process. We are working on this, and that's it. So if you have any question, please say it. Thank you. Any question? I have it appears, okay. Sorry.
Okay, I think you can unmute. Carla, acho que podes.
You know what's the problem?
Okay, just yeah,
Okay.
it's fine. Yeah, because we weren't unable to unmute ourselves so that we could ask questions.
Okay.
So thank you very much, José and Pedro, for this wonderful presentation. I think it reflects very well what we've been doing in TRUSTID. I have a few questions, but I will leave myself for the end. So if anyone else is willing to ask questions, please feel free to unmute yourselves and shoot away. Okay. Or I can just ask mine. So actually, I have many questions, but I'm going to select 3 of them. Okay. So one for both, one for José, and one for Pedro. So my question for both would be: so, what would you say is the most difficult behavior to detect by this type of student monitoring systems?
Sorry, I'm not listening very well. Can you please?
Let me try to rephrase that.
Yeah.
Do you hear me?
There, yes.
So what would you say is the most difficult behavior to detect by this type of student monitoring systems which TRUSTID addresses? So how can students be successful at cheating with these kind of systems?
Okay, from the computer vision perspective, our approach actually, so we detect appearances, right? So right now, we are working on this issue, okay? But right now, if you simply show a picture of someone to the system, the system will eventually log in with that person. Although the second approach actually only validates identities, those information. Okay, so on the second approach, you need to enroll first and give information. So to cheat the system, you need to train the system with wrong information at first. If you train with yourself and try to show an image of someone, the system doesn't work. Although the first approach, in the first approach, that was possible, but so the second version is a bit better. Even so, we are developing solutions that could in practice improve, detects that you're showing a picture, like liveness detection. Like let's suppose that the eyes need to blink and the stuff like that. We are working on that for the next version.
Yeah, that was actually one of the questions I had to Pedro, which is if the system could be fooled by a photograph of the user.
Yeah.
So I think you just answered that.
Yeah.
And José, and from the overall system, and so the system overall, let's say things like second monitor, having another person in the room, checking your cell phone for answers. Mm-hmm. What would you say is the most difficult thing to detect with this kind of system?
Okay, so in my honest opinion, I think one of the hardest things to actually detect is certain and very expert type of behaviors, wherein, for example, let's say like an extremely technical user is able to defeat possibly some of the monitoring capabilities, depending on how expert he can be. Because sometimes you can do tricks, for example, like using virtual machines to try to spoof some kind of behavior. Sometimes you might actually be able to, for example, use these types of applications and try to go around this. We do implement some measures to try to counteract this type of behavior, but it is extremely difficult, and it's mostly a cat and mouse situation where we need to kind of see what the users are actually doing and then implement a solution for it. Because, for example, these are, if I just have simply an application running in my computer, right, it's very hard to detect with any type of a computer vision system if I'm looking away, because I'm just looking at the same screen, right? If I'm looking at the second screen, with gaze tracking or something similar to it, you might be able to catch it. But if it's, for example, on the same monitor, I just have an application, it's extremely difficult to detect. Maybe you are able to detect it via interaction-based, something like with the interactions, with how you're using the windows and everything, but it's very, very, very difficult. But once again, we do have some measures to limit, or at the very least, like prevent those types of things from happening. So, so yeah, that would be for me the biggest challenge in these types of systems.
And we would assume that actually the proctor is a fallback to our system, right? So when the let's say the professor or teacher is actually monitoring the students while doing the exam, something that the system does not detect can be eventually detected as suspicious behavior from the proctor's perspective. So perhaps you can have the proctor actually identifying things that are going on that the system cannot identify. For instance, the student turning away several times to use another machine, for example, or even some kind of interaction going on in the room that is not so easily detected, for instance, using a computer vision approach. So let's say I would say TRUSTID does not assume that the proctor is actually relaxed and waiting and trusting 100% on the system. So we would say probably the system can, let's say, cover vast majority or large number of suspicious behaviors, right?
Sorry, once again, I was having trouble with the sound.
I didn't actually understand the ending as well. Can you
so
just
I will say that the system actually assumes that the proctor is not trusting 100% on it.
Yeah.
I would say it's probably also expecting the proctor to detect some suspicious behavior that goes beyond.
Yeah, of course.
What the system can detect.
Yeah, of course. Even we can only do so much, right? The proctor ideally would have some kind of say on it. Ideally, there's really no way to go around it, right? We can detect a lot of things, but some things maybe you actually do need a second person to detect. And even if you have a second person, you might not even be able to detect them, right? Some people are just can just try to fool the system. Actually, João Marcos typed.
I was
exactly
going to mention that. So in fact, João Marcos told us that in fact the silicon masks, which is a popular way to impose attacks on this front, it's eventually it's a solution that can trick the system. Of course, there are solutions like once again liveness detection. He's actually saying that moving the head movement is also a possible way to deal with that, which is in fact an option. And then that's it. I would like also to add on a thing about the gaze that José was mentioning, because in fact our head pose estimation could in theory give us a general sense where we are looking. It's not really gaze tracking, but most of the time we are gazing forward. So by just analyzing the head pose, we can get a minimal sense of what we are looking. So eventually, right now we are not using this, but of course this is a system that will have more iterations, and we will think on this front to later on. It appears that João has a question. I don't know.
Yes.
João.
First of all, congratulations for your very nice and important work. Before my question, let me just suggest again, based on what José said about interactive behavior between the person that is enrolling and the system. Imagine you can ask, right now, blink your eye, right now, move your face to the left and right. It can be a possibility. But my question is related with the privacy issues. I understood very well why, and I think it was a clever way to try to put everything in the server side, because you don't know about the computing capabilities of the devices. But I guess that for the envisioned application of your system in universities for examination enrollment, etc. I don't know, I'm asking, the system already knows everything about the students, his address, etc., and have a photograph. Why are you so worried about that issue in that particular application?
Okay, I could try to answer first, and the others could add please some information. But the first, the privacy. Privacy is a big deal. Of course, you have right. The LMS system, in your case in Coimbra, we have already has information about the students, but from the software perspective. And if the software needs to be compliant with privacy, it should not publish identity information to the outside. So that's the deal. Right now, on the second version that I mentioned, everything face related is kept on device. So the only thing that the server knows is your email and your name. Right now. Okay, we are just thinking on the software side. So this is our answer for now. But you have also some true feelings about the information. Where is the information? But that's it.
Right.
Yeah. So basically, I think the idea is just trying to mitigate that as much as possible, like the information that the server has. So I don't know. At least for myself, like I think most people would be comfortable sharing their name or even their email. Some like I myself am a very privacy. I do enjoy my privacy. I have relay emails, so I always use like emails that redirect to my actual email. Like I do implement like a lot of these features, and so the idea of having to like upload my data to the server is always a little bit fishy. Like I do believe this is how most users actually feel about this. Like I think if you give the ability to have your data be processed on the server or on the client, everyone I think is going to choose to do it on the client. Even if that comes at the cost of a slight computational overhead, I think this is generally preferred from the user perspective, because it's going to be more accepted.
Yes, understood.
Yeah.
By the way, João, sorry, I don't know if you finished, or do you want to ask another question?
Yes, if I can right now.
Go ahead.
Yeah.
Go ahead.
Yes, more than a question. No, it is a question about the piecewise affine warp. I can see that is a very nice way to go. And Pedro mentioned that will be we can remove the influence of backgrounds. And I wonder if it be useful for many other applications related with face verification. Imagine I can mention, because in the Institute for Systems and Robotics, we are running another projects in compliance with identification documents, etc., where the backgrounds actually must be removed for some processing. Are you being successful using this piecewise affine warp? Did you see the light in the end of the tunnel, and the version 3.0 will be out there soon?
Okay, we are early on the developing on this stage. Of course, I have already used this on other kind of situations, and of course, this is a useful way to deal with the background. It simply removes it. But there's a if you okay, let me show you a few things. Okay, in this case, okay. By showing the full pipeline, this will mean that we need to retrain the network using this kind of information. But it appears that this only makes sense, or it's okay. This might be too much trouble to do it. We can just use the network as it is, using rectangular scaled patches, and use this only on the inference part. Eventually this will operate like this, because there's the gain in performance by training the network with this information is not too much, isn't significant, but is significant on the testing, because on testing, most times testing actually involves testing on several locations. Sometimes we test on multiple locations around the face and average the results. This is the usual way. This approach actually, while it takes a while to compute, it only it prevents this averaging process. So actually, this is done for three purposes: to remove background, to speed up the inference, and to cancel the expressions. But yeah, I think this is I have some promise, although it's not being fully functional right now.
Fantastic, thank you.
Very cool. We look forward to this. By the way, José, you mentioned before, well, that we are aiming towards lower end machines, because we never know. And Pedro also mentioned this in the presentation. We never know what the users have. So one thing that I think it would be interesting to know is which programming language you are using, and if you can provide us some idea about timings on the face detection and face verification process in lower end machines. So and Pedro mentioned something that is very important as well. We are not, we do not assume that people have GPUs. So everything is run on CPUs. So José, if you can shed some light on this, that would be perfect. Thank you.
Yeah. So so we actually were originally running everything in Python, but due to performance issues, and because we wanted to make everything run on the client, we decided to port it all into C++, so that we could have set up a cross-platform compilation system, and try to integrate this more easily into the desktop applications, which had already been developed. When we were doing this migration, I also took an effort into trying to optimize the algorithms that we were using for calculating for using the neural networks, like for doing those calculations. And we did from our results on slightly lower end computers, because I really can't, like, we did some analysis, right? We did a user study with a lot of people participating and seeing what were the best and worst results. And even on the worst machines, we could at the very least analyze an image every half a second or 4 images per second. This was around the times that we were able to achieve. On Windows. On Linux is actually quite impressive, because we are able to almost 10x the speed. From my understanding and from some tests that I did, I believe this is due to one of the packages that we use to accelerate these computations. That there's some differences on how it works on Windows and Linux, and it's much faster on Linux. And so we can do things like, for example, instead of taking 200 milliseconds to process an image, we can almost have real-time real-time face detection and recognition, verification, which is really cool. Yeah, so generally, I think the worst result we had, I think it was around 400 milliseconds, and this is 400 milliseconds detection and recognition. Verification. Verification. Yeah, exactly. We tested with both, with recognition and verification, but I believe the recognition had the worst result, and since we ended up migrating from it, we didn't use it. Yeah.
Very good, thank you.
Yeah, thank you.
So any further questions? Okay, so I would like to thank you presenters and audience once again for the webinar, for being here and for supporting our project. Well, I hope to see you all soon and have a wonderful day. Thank you so much once again.
All right, thank you.
Thank you. Bye. See you.
Thank you all. Bye-bye.